So, we've all been there. You're working on something incredibly important. The deadline is, it's creeping up on you. And suddenly everything just stops.
Oh, yeah, the dreaded freeze.
Right. The cursor won't move. You're clicking the mouse like a dozen times. Nothing happens. And then you do millions of frustrated people do every single day. You just say, the app froze, so I just held the power button until the computer died.
Oh, man, it hurts to even hear that.
I know. Millions of people hold that power button every day. But what feels like a quick fix to, a regular user is actually a sledgehammer to an IT professional.
It really is.
And so today we're doing a deep dive into why mastering the precise language of technology is literally the only way to stop breaking things and, start actually fixing them.
Yeah, because in the technology world, ambiguity and frustration, they cost time and they cost a lot of money. When there is this massive gap between a frustrated user who's just guessing at a problem and a professional trying to fix it, everything just grinds to a halt. So we are bridging that gap today.
Exactly. And to do that, we're pulling insights from Hector Wang-E's ICS class at Leeward Community College, which it leverages the industry standard Professor Messer curriculum.
Which is fantastic source material, by the way.
Oh, it really is. And our goal here, for the learner listening right now, it isn't just to hand out some boring glossary of terms.
No. We are looking at the underlying mechanisms to really understand how standardized terminology transforms you from, a stressed out user into a precision troubleshooter.
Okay, let's unpack this. Because if a user walks into an IT department and just says, the screen is broken,
Right.
they haven't actually described the problem at all. They might mean the physical glass is shattered on the floor.
Right. Or they might mean the computer is turned on, but it's just failing to send a video signal.
Yeah.
And those are two entirely different failures requiring completely different solutions.
Exactly. Standardized terminology eliminates that guessing game. And to build that vocabulary, I think we need to start at the bottom of the technology stack, right? Before a computer can calculate anything or connect to the internet, it needs a physical body.
Yeah, the tangible foundation. And that body really revolves around the motherboard, which is frequently referred to as the system board.
The system board, okay.
Yeah, it is the literal spine of the machine. It is this large printed circuit board that basically serves as grand central station.
Oh, I like that analogy.
Yeah, because every single other component, from the memory to the graphics card, they physically connect to this board so they can actually communicate with one another.
And right in the middle of that grand central station is the CPU, right? The central processing unit.
That's the one.
That is the true brain doing all the mathematical heavy lifting. And I have to admit, I used to make a really classic mistake here.
Oh, really? What was that?
I would point to that massive metal box sitting under my desk, and I would just call the whole thing the CPU.
Oh, yeah. That happens all the time.
I just thought that was the word for a desktop computer. But pointing to the outer shell and calling it the central processor, it's kind of like pointing to a car's entire chassis and just calling it the engine.
That is exactly what it's like.
Yeah.
And the proper term for that outer metal shell is indeed the chassis, or, simply the case.
Just the case.
Right. Because the CPU itself is this tiny chip buried deep inside, sitting directly on the motherboard. So if a user tells a technician, hey, I'm moving my CPU to another desk,
Oh, gosh.
the technician's picturing someone who has literally cracked open the machine, ripped off the heatsink, and is carrying this extremely delicate silicon processor across the room in their bare hands.
Which is just a heart attack-inducing image for anyone working in IT.
Absolutely terrifying.
But, another area where I see constant confusion and where the terminology really fundamentally changes how you solve the problem is the difference between memory and storage.
Oh, yes. This is arguably the most pervasive mix-up in all of consumer computing. Oh, yeah. Because memory, which is known as RAM, or random access memory, it functions as your computer's short-term workspace.
Okay.
It is incredibly fast, but it's highly volatile, meaning the physical architecture of RAM requires constant electrical power to hold that data.
Wait, so?
The second the power fluctuates or goes out, everything stored in RAM is wiped completely clean.
Wow. Okay, so if a photographer friend tells me, hey, I need to buy more memory because my hard drive is completely full of wedding photos,
Right.
they are fundamentally using the wrong word.
Completely the wrong word. They don't need RAM. They need a larger solid-state drive, an SSD, for storage.
Because storage is non-volatile, right?
Exactly. Storage provides long-term retention so that when the power is finally cut, those wedding photos just remain perfectly intact.
Yeah, That makes sense. So you would only ever really need to upgrade your RAM if you were trying to, I don't know, actively open 50 high-resolution photos in Photoshop at the exact same time.
Right, and the computer started lagging because it ran out of short-term workspace.
Okay, got it.
Because purchasing RAM when you actually need an SSD means you haven't solved the underlying issue at all.
Yeah.
You've simply spent hundreds of dollars to just remain broken.
That is so frustrating. But precision matters just as much, I think, when we look at how these components actually receive power and interface with external devices.
It really does.
Because I learned the hard way that cables are not created equal. A few years ago, I was trying to force this old, bulky analog VGA cable into a brand new monitor setup that actually required a digital HDMI signal.
Oh, the classic square peg in a round hole situation.
Totally. And the physical incompatibility was the hardware's way of telling me, hey, the technology has evolved.
Right.
The sources really emphasize how vital it is to distinguish between modern digital video standards like HDMI and DisplayPort.
Which transmit high-fidelity audio right alongside the video, by the way.
Exactly, separating those from the legacy analog connection.
And, the exact same logic applies to USB connections.
Oh, definitely.
I mean, universal serial bus is a bit of a misnomer today because you really must be specific. Standardizing the language means identifying whether you are dealing with the older rectangular type A connector.
The one you always plug in upside down the first 2 times.
Yes, exactly, because it's directional. Versus the modern type C connector, which is reversible and supports vastly higher data transfer speeds. Identifying that mechanical incompatibility immediately isolates the issue.
It really does. So let's talk about the physical forces at play inside that chassis, specifically power and heat, because it takes a massive amount of electrical energy to run a modern machine.
It really does, and it all starts with the PSU, the power supply unit.
Okay.
So wall outlets provide alternating current, or AC power, which constantly fluctuates in a wave.
Right, it goes back and forth.
Exactly. But delicate internal computer components, they require a perfectly steady stream of direct current, or DC power. So the PSU's critical job is to convert that volatile AC wall power into steady DC internal power.
And all of that electrical conversion, combined with the CPU, constantly running millions of calculations, it generates extreme heat.
A ton of heat.
Yeah. So we have heat sinks drawing that heat away from the chips, thermal paste ensuring maximum contact, and fans blowing the hot air out of the chassis.
Right.
But here's where the sources offer a really fascinating troubleshooting insight. Imagine a computer randomly shutting down right in the middle of rendering a heavy 4K video file.
Okay.
The average user assumes they have been hit with a software bug or a virus. But an IT pro looks at that scenario and just thinks about physics.
That's exactly it. Random shutdowns under a heavy, sustained workload are frequently hardware issues.
Really?
Yeah. When a CPU reaches a critical temperature threshold, it initiates what we call thermal throttling.
Thermal throttling.
Right. The hardware purposely limits its own performance or cuts power entirely to prevent the silicon from literally melting on the board. Alternatively, a sudden shutdown might indicate that the PSU is failing and physically cannot deliver the wattage the CPU is demanding under full load.
That's crazy. So it's not a bug at all. It's a desperate survival mechanism.
Yeah, it is trying to save its own life.
But wait, how do you prove an issue is purely hardware related without even loading into Windows? Like, if the screen is black, how do you know?
Well, the system actually proves it for you during the PUST.
PUST.
Yeah, the power on self-test. The very moment you press the power button, before the operating system even begins to boot up, the motherboard runs a diagnostic check on all the critical hardware components to ensure they're present and actually functioning.
It's a brilliant failsafe. Because if the very graphics component needed to show you an error message on the screen is the thing that's broken, the motherboard just bypasses the screen entirely.
Exactly. It uses audio to diagnose itself with beat codes.
Right.
So one long beep followed immediately by 2 short beeps, depending on the manufacturer, that might specifically indicate a video adapter failure.
So the machine isolates the problem for you, confirming you don't need to reinstall your software. You just need to open the case.
You open the case. Now, once the POST is successful, the machine gives a single happy beep, confirming the physical body is healthy.
Okay, a healthy body.
But a healthy physical body with no instructions is just a very fast, very expensive paperweight.
Yeah, totally useless. So the physical body is healthy. It passed the POST. Now it needs to know how to think. Which brings us to the software layer, the digital brain.
Exactly.
Okay.
And the software ecosystem is really divided into two distinct hemispheres. You have system software and application software.
Okay.
Application software includes the programs that users interact with daily. Web browsers, word processors, video games. But these applications are entirely dependent on the system software to function.
And system software is what exactly?
That includes the operating system and your device drivers. The OS, whether it Windows, Mac OS, or Linux, it acts as the ultimate resource manager.
I always wondered about that. If the operating system is the ultimate manager, why does it need drivers at all?
That's a good question.
Why can't Windows just natively speak to whatever printer or monitor I plug into it?
Well, the sheer diversity of hardware makes that practically impossible. There are tens of thousands of different printers, graphics cards, network adapters, and they're all engineered by competing companies using completely different internal logic.
Right. They all speak different languages.
Exactly. The OS cannot possibly contain the native language of every single device ever manufactured. So drivers act as dedicated translation manuals.
Translation manuals, I love that.
Yeah, they sit neatly between the OS and the hardware, translating a generic command from Windows, like print this page, into the highly specific mechanical instructions that a particular Canon or HP printer actually understands.
That translation manual analogy clears up so much troubleshooting confusion for me. Because if a video game crashes to the desktop right after you click the icon, that is an application issue. But if your screen is suddenly stretched out, the colors are all wrong, and you're stuck in this terrible low resolution, your operating system has lost its translation manual for the graphics card. That is a system driver issue.
Exactly. Isolating the layer where the failure occurs is really the essence of IT support. And speaking of foundational layers, we have to address how the OS architecture handles memory mathematically.
Oh, right. The great 32-bit versus 64-bit divide.
It's a huge deal.
Yeah.
Older 32-bit architectures, which are frequently labeled as by 86, they operate under a hard mathematical limit regarding how much RAM they can actually address.
Okay, what's the limit?
A 32-bit OS can only utilize a maximum of about 4 gigabytes of RAM.
Wait, only 4 gigs?
That's it.
To put that in perspective, if a financial analyst tries to load a massive, let's say, 10-gigabyte Excel model into a 32-bit operating system, it doesn't matter if their company bought a top-of-the-line machine with 32 gigabytes of physical RAM installed on the motherboard.
It doesn't matter at all.
The architecture physically cannot see enough memory addresses to hold that data, and the application will just instantly crash.
It just hits a wall, which is why modern computing universally utilizes 64-bit architecture, or by 64, precisely to address these massive pools of memory.
Right.
But the critical rule for the learner here is one of backward compatibility. You can generally run an older 32-bit application on a 64-bit OS.
Okay, going forward is fine.
Right. But it is physically impossible to run a modern 64-bit application on a 32-bit operating system.
Yeah.
Checking the system architecture literally takes 10 seconds, and it can instantly explain why a new software installation just keeps failing at 1%.
That is such a good tip. And, the sources take this concept of OS architecture even further, introducing virtualization.
Oh, virtualization is massive.
Yeah, because the idea of running one operating system on one physical machine is almost quaint in modern enterprise IT, isn't it?
Oh, it really is. If we connect this to the bigger picture, virtualization completely revolutionized the industry by introducing the virtual machine, or VM. Right. A VM is a logical, software-based computer running entirely within a physical host machine.
Like a computer inside a computer.
Exactly. And the software that orchestrates this is called a hypervisor.
Okay.
A hypervisor sits right on the physical hardware, and it carves up the physical CPU cores, the RAM, and the storage, allocating those resources to multiple different virtual machines simultaneously.
The cost savings there are just incredible to think about. I mean, imagine a company 10 years ago running an email server, an accounting server, and a file server.
Yep, 3 separate machines.
Right. Buying 3 massive, expensive physical towers that probably sat idle, 80% of the time?
The least.
Now, a hypervisor lets one physical box run all 3 as completely isolated VMs. It just maxes out the hardware's potential.
And there's another huge benefit. If the physical motherboard dies, the hypervisor can instantly migrate those VMs to another physical server with 0 downtime.
0 downtime. That's amazing.
And that underlying technology is exactly what powers cloud computing.
Great, really?
Yeah. When people say their data is in the cloud, They often picture this nebulous magical entity floating in the sky.
Right, like Wi-Fi magic.
Exactly.
Yeah.
But in reality, the cloud consists of massive, football field-sized data centers filled with physical hardware, using enterprise hypervisors to host millions of independent virtual machines.
Wow.
When a business rents a server in the cloud, they're simply renting a VM.
That clears up so much. But let's bring it back, which brings us right back to our opening hook. Our frustrated user who held the power button because an app on their machine froze.
Right, the sledgehammer approach.
Exactly.
Well, holding the power button forcefully cuts the DC power from the PSU we discussed earlier.
Yeah, you're literally severing the power.
Yes, and if the hard drive is in the middle of writing a critical system file or updating a registry key, when you physically sever that power, you risk corrupting the entire operating system.
You could brick the whole machine just because Word froze.
Exactly. So the professional alternative relies on precision tools, like the Task Manager in Windows or the Activity Monitor in macOS, right? These interfaces allow you to look at every single process currently loaded into the RAM. You locate the specific application that has stopped responding, and you use a scalpel to terminate only that process. The freezing app dies, but the operating system remains perfectly healthy.
That is so much safer. And if the system suffers a catastrophic failure, resulting in the infamous blue screen of death, or BSOD.
Right, the panic screen.
Yeah, a professional doesn't just reboot and hope for the best. They document the hexadecimal error codes displayed on that screen. The OS is explicitly telling you which driver, memory address, or hardware component triggered the kernel panic.
Exactly. It's telling you exactly what went wrong.
So, okay. The hardware is healthy, the OS has its translation manuals, and the apps are running perfectly.
Right.
But a computer that can only talk to itself is basically just an incredibly fast calculator. How does this isolated digital brain actually reach out and connect to the rest of the world?
Well, to understand connectivity, we categorize networks by their physical scope. Starting at the micro level, we have the PAN, the Personal Area Network.
PAN.
Right. This is extremely short range, typically using Bluetooth to connect a smartphone to wireless headphones or a smartwatch. It is a network built exclusively around one individual.
Scaling up, we hit the LAN, the local area network, right?
Exactly.
This connects multiple devices within a single physical footprint. So the router connecting the laptops and smart TVs in your house, that creates a LAN. The switches connecting hundreds of desktops in a corporate office building, that creates a LAN.
You've got it.
Yeah.
And then, when an enterprise needs to connect those isolated LANs together over vast geographical distances, say, linking an office in New York to a branch in Tokyo, they build a WAN, a wide area network.
I gotcha.
And the largest, most expansive WAN in human history is the public internet itself.
Wow, the internet is just a massive WAN. But for data to travel across a PAN, a LAN, or a WAN, the devices involved need an identity, right? The sources outline two distinct types of addresses that dictate how data flows, the MAC address and the IP address.
Yes, and understanding the difference is crucial. So the MAC address, which stands for Media Access Control, it functions as a physical hardware address.
Okay, physical.
Yeah, it is permanently burned into a device's network interface card right at the manufacturing facility. It is entirely unique, and it never changes.
So the analogy of a social security number for your hardware really fits perfectly. It's a permanent identifier.
Exactly.
Whereas the IP address, or Internet Protocol address, that functions as a logical address. It is dynamic, and it changes depending on what network you are currently connected to, much like your current physical mailing address.
Perfect analogy.
But wait, if the MAC address is permanent and unique, why do we need IP addresses at all? Why doesn't the internet just route traffic directly to our permanent MAC addresses?
Well, that distinction really exposes the mechanical difference between local routing and global routing.
Okay, how so?
Think of a MAC address as your legal name and an IP address as your current street address. If you and I are standing in the exact same room, meaning we're operating on the same LAN, I can simply shout your name, your MAC address, and you will receive the message.
Because the traffic never leaves the local room.
Exactly. And the piece of hardware facilitated that local communication is called a switch. A switch connects local devices on a LAN and uses those permanent MAC addresses to forward data to the exact right port.
Okay, I see.
However, if you move to a different city, I cannot step outside and shout your name. I need to know your logical street address to route a letter through the postal system.
Ah, and that postal system is the WAN.
Yes.
To map paths across the broader internet, traversing multiple different networks, we rely on a router. A router connects a LAN to a WAN, utilizing IP addresses to determine the most efficient geographical path to deliver those data packets.
Precisely. And the beautiful thing is you don't have to manually configure that mailing address every time you visit a new location.
Right, because that would be a nightmare.
Oh, it would be awful. But a core network protocol called DHCP, the Dynamic Host Configuration Protocol, handles it automatically. The moment your phone connects to the Wi-Fi at a coffee shop, the router's DHCP server instantly leases your device a valid IP address so you can begin communicating.
Which leads to my absolute favorite troubleshooting superpower from the sources. Because even with a valid IP address, humans don't navigate the internet using numbers. When I want to search for something, I type google.com, not 142.250. Whatever.
Right, because we aren't machines. That convenience is provided by DNS, the domain name system.
DNS, okay.
DNS acts as the master phone book of the internet. It takes the human-readable domain name you typed and translates it into the machine-routable IP address that the routers actually require.
So if a user complains that, the internet is down, you can test this specific mechanism. If you can successfully reach a server by pinging its raw IP address, but your browser fails to load the web page when you type in the domain name, your physical internet connection is perfectly fine.
Yep, you have a DNS resolution issue.
The highway is open, the phone book is just missing pages.
I love that. And identifying where the failure occurs extends to the physical mediums we use too, particularly wireless connections.
Okay.
A WP, or wireless access point, bridges the gap, taking wireless Wi-Fi clients and plugging their data streams into the wired Ethernet network.
And Wi-Fi relies on specific physical radio frequencies, right? Primarily the 2.4 gigahertz and 5 gigahertz bands. And the physics behind these two bands dictate how you troubleshoot a poor connection.
They absolutely do.
Yeah.
So the 2.4 gigahertz band utilizes a longer, wider wave. It travels significant distances and it easily punches through solid walls, but its data transfer speeds are relatively slow.
Okay, so long-range, low speed.
Right. The 5 gigahertz band uses a much tighter, faster wave. It carries vastly more data at higher speeds, but it suffers from severe range limitations.
Because the 5 gigahertz wave is so tight and fast that it physically cannot punch through dense matter, the radio energy gets absorbed by drywall, plumbing, and furniture. So if you are on an important video call and you walk 2 rooms away from your router, causing the call to drop, understanding those frequencies means you don't just blame bad internet. You recognize you are likely on the 5 gigahertz band, which is being absorbed by the physical obstacles between you and the WA.
It changes everything when you know the physics. And to test the quality of a connection, professionals bypass graphical interfaces entirely and use the CLI, the command line interface.
Right.
Typing the ping command sends a tiny packet of diagnostic data to a destination IP address. It confirms whether the destination is alive and measures latency, which is the round-trip delay calculated in milliseconds.
And since we are broadcasting data through the air on these radio frequencies, especially on public WPs in airports or coffee shops, that invisible highway is inherently exposed.
Very exposed.
Which makes understanding security terminology a non-negotiable part of the IT vocabulary.
Definitely. The overarching umbrella term for malicious software is malware.
Malware, okay.
This covers everything from destructive viruses designed to corrupt data, to spyware that silently monitors keystrokes, to ransomware that encrypts your hard drive and demands payment for the decryption key.
But the most successful attacks rarely involve a hacker in a dark hoodie using brute force to break through a firewall, right?
Almost never.
They bypass the multi-million-dollar tech infrastructure entirely by attacking the human element through phishing.
Yes. Phishing is a social engineering attack. It involves sending deceptive communications, like an email meticulously disguised to look like it came from your company's IT department, tricking a human user into willingly handing over their passwords or multi-factor authentication codes.
They don't need to break in if you just voluntarily hand them the keys.
Exactly. Which is exactly why, when utilizing public networks, we deploy VPNs, virtual private networks.
Okay, how does a VPN stop that?
Well, a VPN establishes a secure, heavily encrypted tunnel straight through an untrusted public network. Even if a bad actor is intercepting the Wi-Fi radio frequencies, all they capture is unreadable encrypted noise.
Oh, that makes sense. So using precise security terms allows IT departments to mount the correct defense. If you report that you have a virus when you actually entered your credentials into a spoofed phishing website, the security team will waste time running malware scans on your chassis instead of immediately locking down your compromised user accounts.
Right. Precision saves the day again.
So what does this all mean? We've traveled from the physical motherboard all the way up to virtual machines running in the cloud. We routed data using MA addresses on local switches and IP addresses across global routers.
It's quite a journey.
It is, and internalizing these terms, it isn't about memorizing flashcards for a test. It fundamentally changes how you interact with the digital world.
It really shifts your perspective from being a passive victim of technology to an active, capable troubleshooter. Understanding causality, knowing that a heavy workload causes thermal throttling, or that a 32-bit OS physically limits memory allocation, it allows you to solve the root problem rather than just reacting to the symptom.
It is the foundational stepping stone for achieving higher-level mastery, like pursuing the CompTIA A+ certification. You must be fluent in the vocabulary before you can write the poetry.
I love that phrasing.
We started this deep dive with a frustrated user holding the power button, just hoping a forced shutdown would magically fix their problem. By replacing that ambiguity with precise language and diagnostic tools like the task manager or the ping command, you save immense amounts of time, money, and sanity.
You really do. And, this focus on precise language leads to a really intriguing consideration regarding the future of human-computer interaction.
Wow.
Where are we headed?
Well, we've established that human ambiguity, guessing at problems and using vague descriptions, it currently causes massive inefficiencies and system crashes.
Right.
But as we look over the horizon, we are entering the era of brain-computer interfaces, where direct neural links will allow human thought to instantly manipulate digital systems.
We are bypassing the keyboard entirely. Exactly. So if human-to-human tech ambiguity costs us so much today, what happens when our unfiltered thoughts become the direct input method?
Oh, wow.
Will humanity need to develop a completely flawless, standardized internal language to interact with these systems? Because if you encounter a frustrating digital roadblock in the future and vaguely think, ooh, just kill it, you might not just forcefully close an application, you might inadvertently crash the very digital infrastructure your mind is plugged into.
From holding the power button in a panic to accidentally thinking your system into a crash, that is a wild and terrifying concept to leave on. Thanks for diving in with us, learner. Keep asking the right questions and keep using the right words.